Hello and welcome to Lecture 29, Introduction to These. Not these nuts, but differential equations. And I promise you, they sound difficult. Probably people have told you they're hard and everything. What? That came out wrong. But differential equations essentially aren't that difficult. You just have to look at them from the right perspective. Of course, every problem can be made difficult, but just look for the first two examples that we solve. I promise you, you will see that it's not difficult at all if you know integration. But yes, so what are differential equations? It's basically an equation involving a function and its derivative. So we remember derivatives. The formula of a derivative of some function is the slope of it. But this in itself is a differential equation already because it is an equation, it has a function, and it has its derivative. So in this video, we will familiarize ourselves with various simple differential equations that we can come across, and maybe some rules that we can solve, so we can solve them even easier and faster next time. Yeah, so you may be asking yourself, what's so different about differential equations from normal equations? Well, normal equations tell us, the value, while differential equations will tell us the behavior. For instance, we can use differential equations to determine the behavior of a system and what value it will have at a certain point or time. So where normal equation, for instance, gives you the path you have to take, differential equation will give you directions for each single step, and all you have to do is use those steps to build the path yourself. Kind of. In reality, most systems are not defined by formulas, but by their change. So using differential equations, we can personalize the basic equations to the change the system experiences. So, for instance, let's say the temperature is a certain function. We manipulate a couple of formulas from thermodynamics or something, and we get the function. That function will behave differently. Like overall, if we get the final formula, that formula will be different for the cup of coffee. We'll have a function g of x. If we have a boiler down like in the basement or something for heating up your water, it will have a different formula. And let's say the sun, it will have its own formula, but they will all originate from the same formulas. So like the same equations from physics. So the heat transfer, the property, the heat conductivity and stuff like that. All of that combined depends on the system. That depends on how open it is. Depends on how isolated it is. The medium around it, like the vacuum of space, conducts heat much less than the air, etc., etc. So differential equations allow us to personalize to each specific situation. So let's say you're studying motion and you don't start with position but with velocity, the speed with which the object is moving, because that will tell you how position changes. In population models, you don't really care about how many individuals there are to set the model. You care about how fast the number is changing and in which direction. So you don't need one value, you need a list of values over a certain interval of time. And then you develop a rule. Sure, if you want to know the number of individuals at any point, you can solve for that at any desired time, but looking at the dynamics of the system rather than the stationary position allows us to figure out a rule which then should apply to the entire dynamic if we did it correctly. So we see it all boils down to the rate of change, and what is that? What's exactly what they describe? I think that's Englishly correct. It's probably not, but I'm not English, so... But yes, here will be a list of a few different types of differential equations, starting off with ordinary differential equations, which is an equation involving an unknown function of a single variable, its independent variable, and its derivatives. So something like this. So we have a certain function, the variable, the derivative, and this is just one example of an ordinary differential equation. Oh. Next up are first order differential equations, which are going to be the majority of those that we need later on, and they contain only the first derivative. So this is an example of one such. We have a sort of function that we modified with the x, so that's not important currently here. We have the derivative of that y, so dy over dx. And we could rewrite the first term as y prime to show it better, like here. And then we have the independent variable. Then we have second and higher orders of differential equations, and as we can speculate from their names and its similarity to first order, that they will have a second or higher derivatives in them. So we guessed correctly, and this is one such example. Of course, we have linear differential equations because the linear functions are everywhere, and they are equations where basically the unknown function and its derivatives appear linearly, so to the power of 1. We see that this is also a first order differential equation because, well, certain types can coexist, but eventually you get to a point where you've solved so many that you don't need to be like, oh, that's a first order linear differential equation with some other properties. No, you're gonna solve enough examples that you're gonna know how to solve them, even if you can't name it itself. So like you're like L'Hopital's rule. You can forget how it's called, but you know that when it's like limit of something of infinity over infinity, you use that rule. Okay, okay. I hope that I can at least give you that much knowledge into solving basic differential equations. Of course, there's plenty other differential equations. So ordinary differential equations, partial differential equations where we use partial derivatives that I only mentioned. I did not truly cover because there are an honorable mention. We have linear differential equations where y is to the power of 1. We have non-linear, so products are powers of y or derivatives. So like we have y to the power of 2. We have homogeneous, where all y terms are on one side and 0 is on the other, and no homo or non-homogeneous. I cannot speak that word, where there is no 0, so we have y is isolated on one side and x is on the other. Of course, there's a few other differential equation types, but they're not as important for us. So let's start with first order D's, and as I said, it only involves the first derivatives. They are the simplest ones. Basically, we already solved some when learning differentiation. So there's just a few examples of them. In the first, the change is dependent on the position at which we are observing the system. So we have a certain function, and then we draw the slope at two random points. We see that they change depending on the x value at which we read it. In the second, that change depends on the current value. So the higher the y, the higher the slope. And the lower the y, the lower the slope. Kind of, yes, of course. But yes, we will dive more into these two later. And the last type it has both of these effects combined. So let's see how to solve the first two. This one I have an animation or simulation, whatever you want to call it, that I will overlay in the editing. But yes, let's see the first two and what each solution means. So, as promised, solving the first order differential equations. So, differentiation meant finding the slope. For differential equations, we are finding the function that follows the shown rule. So, what we're given is a rule, and we have to find the function that follows that rule. So, the equation presented is the rule, and we need a function, so more often than not, we will be integrating. So, this is our first differential equation that we have to solve. So, we will reverse the differentiation with integration, and hopefully we know how to do that. Some sketches already exist because I failed recording before because I was muted. But basically we have a certain slope, derivative of a function, that is dependent on some x. Then we will use methods like integration, taking a derivative or differentiation, and some other techniques that we may cover in physics chapter to find the function, like the original function that can be applied to the example. So let's solve it. First, we'll carry dx to the right, and we get dy equals 2x dx. We have two differentials separated on each of its own side, and we can integrate each side separately. We will be using indefinite integrals, since we do not have defined limits to the current system or problem, but we will touch more on those in later lectures or in physics. However, I will show you how to work with conditions like at the start, at the end of the measuring, without having to use the limits of integration, simplifying your solving process. So, we integrate, and now I remember I said a while ago when we integrate both sides we don't need the plus c, and that is only true sometimes. More often than not you will need it. So because I took that example from a certain book, and they said in that specific example the constants cancel out. In other examples, the constants will stay, and from now on we will be writing the constants unless the example itself will provide information about it. Hopefully I remember that too when I make the future lectures. But yes, each of the sides gives us a plus constant, so let's just say we combine them into another constant and move them both to the same side. We could say integrating dy gives us a capital A constant, and integrating the x part gives us a capital B constant, and when they move together to the same side, they become a plus c. However you want to imagine it, to understand it, as long as this helps, this is our result. We see that for the basic first order differential equations, we simply integrate or isolate one variable on one side and the dependent variable on the other, and then integrate, and that's it. It's really not that scary, and if you stuck here, as I promised, I'll put the timestamp on the start, just so you can skip here and see how easy this actually is. And if this wasn't easy, you can just jump back to my integration lectures, check like 10 minutes of each, 5 minutes of each, and just like you will be able to understand it, I promise. And if you can't, comment down below, I will gladly help you out, because I genuinely want to help people learn. That's my whole goal of this channel. I don't care about the money I can make, as long as you guys can make. I'm gonna make a practice test for physics. I'm already making it. The common problems, the shapes of formulas that we're gonna have, so you can learn to isolate different variables from such systems, so it's gonna come naturally to you. So be on the lookout for that. Still a month away from now, I think. A month and 2 weeks? Anyway, time for our example. Well, first one was a demonstration. This is an example. We won't solve as many, as this is basic integration, so we can move forward slightly faster to the harder things. But yes, we have dy over dx equals 3x squared plus 2x. We will move our dx to the right. We will integrate, and we know that this basically gives us this. And then we use the power rule, so we raise the exponent by 1, and then divide by the new exponent. We get x to the power of 3 plus x to the power of 2 plus c, because both constants combine on the same side. And this is our solution. Now let's say we had a condition for this example, that our function at x, let me circle this. So this is our condition that we were given, that our function at x equals 1, the function itself will equal to 2. So at, I don't know, time is 1 hour, our speed will be 2 kilometers per hour. For instance, that's just a basic example. Don't take it literally, because that's wrong, but sort of demonstrates. It's wrong for this exact formula. But yes, using that, we can solve for the c. So we will insert the y value and the x value. So 2 equals 1 to the power of 3 plus 1 to the power of 2 plus c. And then we subwrite it, we add all of this together. 2 cancel out on both sides because we subtract by 2. And we get 0 is c. And we get that the c in this specific example was 0. So in physics, if we have a problem like this, we would get the function that describes the behavior of some system, and then the condition would tell us that at the time 1, position 1, or whatever we have instead of x, the result of that function would be 2, as I tried to demonstrate at the start. Then we would solve for the constant, or constants, because there can be multiple of them, and then we could use that formula for any other time, position, or to just determine at what time do we reach that temperature, for instance, which we will do in physics. So far everything worked because the derivative depended only on x. But yes, c for when y when x is 1 is 2 is 0. But yes, so far everything worked because the derivative depended only on x. But what if the function starts affecting its own rate of change, meaning we have a y value in the same equation as its derivative? That's where things become more interesting and more common in physics. So here is a sort of a key model for this example, where we have a change of y in regards to change of t to, let's say, time, which equals k times y, where k is just some constant. So the same y, the change of which we're looking at. But yes, I swapped the x for t just to ease you into physics, where we won't always have x's. But yes, the derivative of y is, this is missing the correct symbol. It should be like this symbol, or if it's like that, it should be ky. So these are the two more correct markings. I kind of made a mistake here. So let's look at it intuitively. If the value big, then the change big. While if the value y small, then the change small. Just looking at the formula, if we can imagine that the left part is a slope at a certain point. So yes, if we imagine the left part as a slope at a certain point, as a function of the y value, the higher the y value, the bigger the slope or the change should be. Lovely, right? But that property is interesting, isn't it? So here is a MOG graph. Purple lines represent the slopes at a specific point of the function, and the red dashed line indicates a sort of turning point under which we have low y's and above which we have high y's. So big Y, big slope, small y, small slope. Because hopefully we still remember that the slope is the change of y divided by the change of x. So this is the change of x, and this is the change of y. So we see that this is much lower than this is, while in this example, change of y is much higher than the change of x. That's horrible, but ignore that. So this y1 and this y2, we see that y1 is much greater than y2. Okay, this looks horrible, but this one coincides with this one, and this one is this one, so kind of like that. So painfully dragging my mouse, I can draw a sort of this graph. Of course, where it is facing depends on k. So if k is less than 0, we have the k, and the slope will be negative. And if y approaches negative infinity, then the y approaches negative infinity, and if k is greater than 0, we get something similar to what I sketched, because, well, I'm sure as hell that this doesn't count as a drawing. It's more of a sketch. But yes, back to the graph, we can say that it's increasing exponentially, but not just any exponential graph, the exponential graph, also called natural exponential function, the one with base being e or Euler's number, right here. So let's see how we actually get that function. So first things first, let's bring the same variables to the same side. So we divided both sides with y and multiplied with the dt, so this fella moves to the right, and this fella moves left, and we get this. Now we integrate. We set this integral, and we remember. We have two separate integrals. The right one is simply k times t plus c, and the left one, we remember, gives us a natural logarithm of an absolute value of y, because, well, dx over x, the integral of that, if we use the power rule, it becomes x to the power of 0. We don't like that, because then we would have x to the power of 0 divided by 0, and that's undefined, so natural logarithm it is. But yes, and of course, I combined both constants into 1. Now, to get our y, we anti-logarithmize, or however that's called, exponentiation or whatever. Basically, e to the power of this thing, and we get y equals e to the power of kt plus c. Now, we have e to that power of some sum, power of sum. So we use the basic multiplication rule, which states that if we multiply two of the same numbers raised to different exponents, we can rewrite that as the same number as base to the power of the sum of the two exponents. Oh, the exponents can be the same as well, my bad. So here we can rewrite this as this. So the product of two separated ones. So e to the power of kt times e to the power of c. But that last part is a constant to the power of constant. So we will, once again, just write it as a single constant, as it does not change throughout the experiment. So we get c times e to the power of kt. This is our formula, this is our key model, this is our rule, this is sacred. I would say remember this, but if you know integration and you have this basic shape, this is easy. You just reorder them, set the integration. These integrals are not hard. Like, these are the basic integral tables. That's why I'm saying they're not hard. Okay? So if you put some time into integrals, integral tables, this is easy. And then you just do e to the power of natural logarithm of y equals e to the power of the entire right side. And then we know that e to the power of natural logarithm, because this is rewritten as log of base e of y. We know this basic property that if we put this base as the base of the exponent and then raise it to that, we get just as the basics. Like, skip back to my logarithms lecture if that still troubles you. I think I explained it. If I didn't, comment down below. I will explain it, I promise. Anyway, yes, this is our formula. This is the solution to such a simple differential equation. So it's all about integration and moving the same variable to the same side, etc., etc. Of course, we will go through other methods and steps of solving more thoroughly in the next lecture, and the third one, but hopefully this illustrated the point that I wanted to make. Now remember, when I gave a y value at a certain x, we can treat that as a sort of initial condition. But usually, as the name suggests, it is a state of a system. So let's say we have a cup of coffee. So our problem could be described that our coffee, when it's served, has a temperature of about 60 degrees Celsius, which is 140 degrees Fahrenheit for those of you using the weird units. And then we would be given a differential equation or even make it up ourselves. So we would then solve it, I don't know, find the temperature of the coffee after some time. So here our 60 degrees would be a very helpful information because it provides two values, the temperature and the time at which we have that temperature. Why is that important? Because as we saw before, the constant present makes it hard to solve it as we have yet another unknown value. So with these conditions we can solve for that first and then use that constant to solve for our problem. So basically solving the problem with extra steps. So to practice a bit, here we have our very basic differential equation and an initial condition for it. So first we will isolate the variables, moving dx to the right. We integrate, and we have the formula we got before. Now we insert the initial conditions to solve for c. We insert that, and we get that c is 1. And we get our complete formula. We get our complete formula. This is it, and we'll just, for time 12, we can put 12 squared plus 1 is 145, and that would be our result. It's that simple. Okay, but why initial conditions? Well, so they help us determine the c, but they can't be that important, right? Unfortunately, or fortunately, they are very important, because a different set of initial conditions can change the function, behavior, and even result by a lot. So let's imagine a coordinate system. A differential equation gives you a slope at every point. Here I drew a few red arrows symbolizing the slopes and how they can be different depending on where they are. Those slopes are drawn before solving the equation given, of course. After solving it, you get the function that will perfectly fit the slopes we can draw before. The coordinate system with the slopes fitted on it is called a slope field. However, we need more of these for every single point. And then we just take the initial condition and follow where the arrows point. So the initial condition here and here will take a different course of action. So we see that the green and purple functions both behave in a relatively similar way. They are both approaching the same values at the end, but before that they are far apart. This is a very poor sketch, so let's check the programmed visualization or animation that shows this pretty much perfectly. As we can see, there is a differential function on top, and it describes a slope. So I think it's the difference of x and y. We see that it's just it's drawing all the arrows, and if at any point you take the x and y values of that arrow, you can just plug it in together and just see that it's correct. And then after that, you can draw so many different functions depending on the point you start. Of course, they will lead to roughly the same endpoint because, well, it converges. But depends on where you start can change the system a lot. And that's what we will do in physics and chemistry a lot as well, because we will see how systems behave, especially in extreme conditions. Unfortunately, the differential equation in the video is not solvable to us for now, But we will learn the tools either next time or on the third lecture on this topic or even later to make sure we are prepared for physics and any other real-world applications. But yes, for those of you with a bit more knowledge, it will be a type of U substitution. Anyway, here is the mini test. I made it quite easy, to be honest. We are gonna be working with units now, so be careful. Here we want to just get the function. I forgot to add it. So third problem wants the function. And here you need to watch out for what units the constants have. But this will be it for today's lecture. I hope everything was understandable. I am still slightly sick. Nose is full and my throat hurts, so as you can probably hear. But yeah, I hope it goes well solving the mini test. If you have any questions whatsoever, please don't be afraid to ask down below. I think one person will make it to the end of this video per 1,000 views. So if you see this, I appreciate you, man. I love you. Thank you so much for staying here until the very end. And I'll see you all on our next quest. Bye.